Next, we'll apply what we have seen to study AB recurrent sequences once again, namely to study how they behave modulo a certain number m. Periodicity of linear recurrence, so of AB recurrent sequences, modulo m. We begin by recalling two problems that we have seen before. This was an example and this was a homework exercise. So this example said that essentially the sequence of remainders modulo 2 of the Fibonacci numbers is 3 periodic. The remainder modulo 2 depends only on the divisibility of n by 3, so it repeats itself every 3 values. This exercise, this is the homework one. This one easily yields that the sequence of remainders modulo 5 it's also periodic. To be more precise, 20 periodic. Because this here repeats every 5 values of n, and this, if you look at it modulo 5, it repeats every 20 values of n. Now I claim that this can be generalized. So this is part of a bigger pattern. And let me state it in a reasonably general form. There is a slightly better version in the homework exercises. You will have to do it on your own. Let m be a positive integer. Let a and b be integers such that b is co-prime to m. Let x0, x1, x2, and so on be an AB recurrent sequence of integers. Prove that the sequence of remainders of this axis modulo m is k-periodic for some k between 1 and m square. And notice that you cannot that easily predict what this k will be in advance. So here, for example, it was 3, here it's 20. On the homework, you will see that you can actually, this m square is too big. You can do it with m square minus 1, but you cannot make it smaller. M square minus 1 is achieved, I think, for m equals 3 or something like that in the Fibonacci numbers. So I will give an incomplete solution here, and you will have to complete it on the homework. That's one exercise. So what is the idea? While an entry of our sequence is not uniquely determined by the previous entry, xn minus 1, a pair xn, xn plus 1 of two consecutive entries is uniquely determined by the previous pair xn minus 1, xn. Namely, if you know xn minus 1 and xn, you have so you already know xn, and then xn plus 1 is a xn plus b xn minus 1. So if you know this pair, you can get to this pair. This was already the idea behind our matrix approach. And now we will reuse it again. Therefore, the pair xn%m, so the remainder xn plus 1% m, is uniquely determined by xn minus 1% m and xn% m. Namely, you just take remainders here. Now you have to think a little bit, because you don't know xn and xn minus 1, you only know the remainders. But because we're taking the remainder at the end, so we're working modulo m, you can replace those numbers by the remainders. So the whole idea is, if you're interested in the remainders of the entries of your sequence, it's enough to just work with pairs of consecutive remainders. If you know one such pair, you can basically go further and further. You don't need to know all the previous values. So I'm going to rewrite this. I'm going to rewrite this as xn%m, xn plus 1%m is a certain function of the previous pair, xn minus 1%m, xn%m, where f, let me say for now, from z cross z times z cross z is the map given by f of, and now you just generalize this formula to any two values. So you have f of pq is q aq plus bp percent m. So basically f is the algorithm how you can compute these two numbers from these two numbers. The second one goes into the first position, and the new second one will be made from the first and second using this recursion formula. Now, noticing that we're only looking at remainders modulo m, so we don't need to define this on the whole integers. We can restrict ourselves to the numbers that actually appear as remainders modulo m. And these are the numbers between 0 and m minus 1. Nothing else will appear. So let's see what we know about this f. I claim the following. Claim 1, the map f is bijective. This is just saying if you know q and this remainder, you can reconstruct p and q. And as for q, this is obvious. You can reconstruct q just by taking it from here. But to reconstruct p, you will have to solve this equation for p, modulo m. And this is where you have to use that b is coprime to m. So the details of the proof are an exercise on the next homework set. Claim 2, this is what I just said. That this f is really the dynamics of this pairs of consecutive remainders. And finally, claim 3 is that any such pair is f to the n applied to omega. What is omega? Omega is the pair of the first two remainders. So you take the first two entries and you take the remainders modulo m. That pair will be omega. And the claim is if you want any two consecutive remainders, you just apply f n times to this omega. And this follows from claim 2 by induction. And again, the details are an exercise. So what do we get? Now we have a bijective map f. So it is a permutation of the set of all possible pairs. And how big is the set? It's an m square element set. Now recall this previous theorem about permutations. I'm going to copy paste it here. So one of the theorems from the previous section, we can apply this now to x being the set, f is f, little x is omega, and n has to be m squared because this is an m square element set. Yields that, and now I just copy paste, there exists a number k between 1 and m squared such that fk of omega is omega, and furthermore, the sequence is k periodic. Now, what does this mean that the sequence is k periodic? It means that these pairs of remainders repeat every k steps. So that is this pair, well, let's say it this way, fi of omega is fi of k plus k of omega for each I in n. In other words, because of claim 3, you can rewrite fi of omega as xi remainder m, xi plus 1 remainder m equals the same for I plus k. And now two pairs are equal when their first entries are equal and their second entries are equal. So let's look at the first entries. This means that xi percent m is xi plus k percent m for each I. But this means that the sequence of remainders is k periodic. and we're done. So just to recap, the sequence x0, x1, x2, and so on is usually not periodic. We've seen some periodic recurrent sequences, but the average recurrent sequence will just go to infinity in some exponential way. Like the Fibonacci's are not periodic. But if you restrict yourselves to the remainders are actually, they have an advantage. They're stuck in a finite set between 0 and m-1. Even the pairs of consecutive remainders, they're still stuck in a finite set, namely the set 0, 1 to m-1 cross itself. And so when you follow the sequence from start to finish, so to speak, even if there is no finish, you will always just keep walking around this finite set. And you keep walking deterministically because each next pair is uniquely determined by the previous pair. And as we have seen here, walking through a finite set deterministically gives you a periodic sequence. And if this deterministic procedure is a permutation, this periodicity starts right away. And this is exactly what we apply to those pairs of consecutive remainders. So those pairs behave periodically. And therefore, the single remainders also behave periodically, which is what we wanted to show.